Okay, here are the solutions to the activity for section 3.7. The first problem says a Norman window is constructed by adjoining a semicircle to the top of a rectangular window. Find the maximum area of the window if the total perimeter is 16 feet. Okay, so the thing we want to maximize is the area. And so we need to find an expression for the area. In the area, we need to break into two pieces, but we've also been given information about the perimeter, right? Okay, so we can break this window into two pieces. It's a semicircle and a rectangle. And if we look at the semicircle, its area is 1/2 pi times the radius squared, because it's half the area of a circle. And its perimeter is 1/2 2 pi r, because it's half the perimeter of, or half the circumference of a circle. And the purple line here is not counted in the perimeter. Okay, and so then the area of the rectangular piece is 2r times h, and the perimeter is 2h, that's the two sides, plus 2r, not counting the fourth side, so that just counts three sides of that rectangle. Okay, so now we can get expressions for the area. It's 2rh plus 1/2 pi r squared, that's adding the pieces together. Same thing for the perimeter. And then what do we know? We know that that perimeter, after we simplify it, is equal to 16. And now here the algebra battle begins. We can solve for h in the expression for the perimeter here. And then we can take that expression for h back up into the expression for area here. And that gives us area as a function of r. We can do some algebra to simplify it a little bit. We don't have to do a bunch because we're going to take its derivative, set that derivative equal to 0. And we get an expression for r as 16 over pi plus 4. We can then go back up and solve for h. It simplifies also to 16 over pi plus 4. We've been asked for the dimensions though, so the dimensions would technically be 2r by h. And so 2r is 32 over pi plus 4. You could check with the second derivative that this does give you a maximum. I ran out of space here, but you could take the second derivative of area. You'll only have some constants there, and you can see that you get a maximum because the function is concave down. All right, the second problem is similar to the second one in the introduction. A rectangle is bounded by the x-axis and the semicircle y equals square root of 25 minus x squared. What is the maximum possible area of the rectangle? Okay, so I've drawn the rectangle in blue. I've labeled a random point on the x-axis. So that point would be the point then x comma whatever the output of the function is, which gives the height of our rectangle as the square root of 25 minus x squared. And it gives the width of our rectangle as 2 copies of x. Okay, so the area then is that height times width, so it's 2x times the square root of 25 minus x squared. We can rewrite that ever so slightly so that we can use the product rule and the chain rule to take the derivative. So we set that derivative equal to 0, and we're looking to find a maximum, and we know that we're looking for x's that live within this window, right? Because that function hits the x-axis at 5, and I've labeled x on the positive side of the x-axis. Okay, so we can factor here. This factoring is going to come up in a ton of problems. So we can factor actually a 25 minus x squared to the negative 1/2 out of both of these terms. So we're factoring out the smallest exponent there, which is negative 1/2. We get negative x squared plus 25 minus x squared then to the first power. And that first piece of this will never equal 0, so we just have to look at the second one, and it's not so bad to solve. So we get x is plus or minus 5 over the square root of 2. So we choose the positive one, and we look at this, and we get that when x is 0, that's an option, right? It's one of our endpoints. The area is 0. When x is 5, the area is 0. And when x is 5 over root 2, we get 25. So that is our maximum area. And the question asked, what is the maximum possible area? Okay, you guys may have to pause this video at times to check out some of this algebra, but I'll be happy to answer questions on it. Okay, the last says 2 posts, one 12 feet high and the other 28 feet high, stand 30 feet apart. They are to be stayed by 2 wires attached to a single stake running from ground level to the top of each post. Where should the stake be placed to use the least wire? Okay, that one takes some mouthful. So we have 2 wires. I've drawn them on the left. Or sorry, we have two posts. They're 12 feet high and 28 feet high. Here are our posts right here and here. They're stayed by 2 wires at a stake, which I have drawn there. I know the distance between the posts is 30. So I just chose to call this first distance from the shorter post to the stake X. Could have called it anything or either side, but that leaves this other distance from the stake to the longer post. Well, it's got to be whatever's left from the 30 when we take away the X. And then I called those things wire 1 and wire 2. And we want to minimize the distance. We want to find the least wire. So we want to minimize wire 1 length plus wire 2. Okay, so we have two right triangles here, right here. So we can use the Pythagorean theorem. We know x squared plus 12 squared is wire 1 squared. And we know 30 minus x squared plus 28 squared is wire 2 squared. So we can solve for wire 1 and wire 2. They're already in terms of one variable x, so that's good. We don't have to do any other solving here and rewriting in terms of another variable. The total wire, which is the thing we want to minimize, is going to be the sum of those two expressions. Again, there's some temptation to simplify things, multiply them out. Just don't do it. It'll make the algebra a little neater in the long run. So we take the derivative using the chain rule a couple of times. Here we're going to need the chain rule. So there is the derivative using the chain rule. We see we have to be a little bit careful with the chain rule here when we take the derivative of that thing inside. The derivative of 30 minus x is negative x. That's where this negative 2 comes from. That's going to be key. So we simplify these things a little bit to get this new expression for w prime. I move the square roots down into the denominator. And we need to know when this is equal to 0. And we know that x must live between 0 and 30. I guess technically it could be 0 or 30 could be an option here. I guess technically these could be equal to. Seems unlikely. All right, so when is it equal to 0? Well, it's going to be equal to 0 when these two terms up here are equal to each other. And so we set those two terms equal to each other, square both sides, cross multiply, distribute the x squared on the 144. And then it looks like we get a bunch of algebra. We lose the x squared times 30 minus x quantity squared terms from both sides. And then I rewrite both sides of the equal sign as something squared, and I can factor those as the difference of two squares. And we can end up factoring this thing. Looks like 360 minus 40x times 360 plus 16x. Set those equal to 0. And we get x equals 9 or x equals negative 22 and a half. Well, we know x is going to be positive in this case, so we choose 9. And that gives us our possibilities as 0, 9, and 30. And so then we got to check. We don't think 0 or 30 are going to do the job, and we see that we get a minimum when x is 9 at 50 feet. So our minimum wire was x equals 9 and 50 feet.